Hello everyone, welcome to the lecture series on computer vision. This is Saina Chaitanya, Assistant Professor from Department of ECE, RGKT Basar. So for today's class, we are going to discuss about the SIFT algorithm. So what is this SIFT? SIFT is a scale invariant feature transform. It is basically a detector as well as it is also acting as a descriptor. We know that the Harris operator is not so invariant to scale. So it necessitates us to develop an operator or an algorithm that is invariant to the scale as well as the rotation. So here SIFT creates a descriptor that is robust to the affine variations corresponding to typical viewing conditions. So it is one viewing condition, right? And it is also one viewing condition. So it is robust to the affine transformation, which may be a rotation or scaling or translation. Right. So SIFT is a technique that is useful for detecting the salient stable feature points in an image, which are nothing but the interest points in an image. So SIFT here is providing us a set of features that is characterizing or describing a small image region around the point. This point may be an interest point. This is invariant to rotation as well as the scale. So I will explain you this, how it is invariant to rotation and scale. Now you can see. So I have here a point here. So there may be a point and there may be a point here. So the SIFT, what it will be doing here, so it is providing a set of features. So this is nothing but it is a set of features that this feature is developed by characterizing a small region around this point such that this feature, that means this feature is invariant to rotation. That means here I have rotated, right? Because I don't feel the same scene here and here. Some tilt had happened between these two images, right? So that means if I zoom this region, I will be having this kind of scenario. And so this SIFT is providing a set of features here. So it is describing a small image region around that point, and based on it I am getting the features, and these features are invariant here to rotation as well as the scale. Okay, so like for example, like I have said you that the SIFT algorithm is mainly to detect the stable points or the salient points in images. So here I do have two images, you can see here, and these are the two images, and this is one image and this is one image. This image is taken with different lighting conditions, and this image you can see here. So it is captured from the front view and it is captured in a diagonal view or a side view, and this image is a rotated version of this image, right? Okay, so the main agenda of the SIFT algorithm here is it is useful for detecting the stable points or the interesting points in the images such that I can able to determine the correspondence between the two given images. So if it is finding out the stable points, means obviously the features will be getting developed, and these features are not going to change with the object pose like this. So the object pose, it is not going to change, or like scaling or like illumination condition or blurring or any noise. Okay, this is the main advantage of the SIFT algorithm. Okay, now in order to progress or move ahead forward in the SIFT algorithm, we need to follow the following steps. One is the scale space peak selection. So this scale space peak selection is useful to determine the approximate location and the scale also of these feature points. Okay, of course these feature points are nothing but they are always a stable points or a salient feature points. These are nothing but a key points in the given input image. Okay, now the next one is key point localization. So what actually this key point localization here is, it is we are refining the locations of the key point and also scale. Okay, so this is about the key point localization, and next is orientation assignment. That means we are determining here the orientation for each and every key point or the interest point in the given image. And the last one is the key point descriptor. So it is useful for determining the descriptors for each and every key point. So what actually this descriptor, you will be knowing it at the end of this topic. Okay, so in brief, the scale space peak selection is nothing but it is the scale space extrema, that means maxima or minimum, right, detection. It is this first step is useful to find, or it is useful to search over the multiple scales and image locations what will be where I can able to find the extremas. And coming to the key point localization, it is where we will be fitting a model to determine the location of the key point and scale of it. Okay, what will be its scale. Okay, that means where we have to select a key points based on the stability. So if a particular interest point is stable, means definitely I have to find what its location as well as the scale, its location and scale. And the next one is the orientation assignment, where we will be computing here the best orientations for every key point. Okay, and the last one is a key point description. So it is we use these descriptors. So I will explain you about the key point descriptor in detail in the upcoming slides, right? Okay, let us see about the first step, that is scale space peak selection. So what actually this scale space peak selection is? So the scale space of an image is a function L that is produced from the convolution of Gaussian kernel at different scales with the input image. That means it is nothing but L equal to G into I. So that is what the entire statement is giving me the meaning. So this scale space is separated into octaves, and the number of octaves and the scale depends on the size of the original image. Okay, so we generate several octaves of the original image. Each octave image size is half the previous one. So what actually this octave and what is this scale being mentioned many number of times, right? Okay, now if you have understand for the first point, that is the scale space of an image is a function L equal to G into I. Okay, the next thing is scale space is separated into octaves and scale here. So you can see here I am having some original image in this manner. So this original image is scaled many number of times, right? So that means here it is my first octave, it is my second octave, and it is my third octave, and it is my fourth octave. So by seeing the slide itself, you can observe that the size of the image in the second octave is half that of the first octave, and the third octave image size is half that of the second octave, and the fourth octave image size is half that of the image size in the third octave. So this is about the octave, and you can see in a given octave some kind of clarity is missing in the images. That means here scaling is done. So these are 4 different scales, and these are some different scales. This is some different scales. So that means here what is happening, scale space is separated into octaves, and the number of octaves and the scale depends on the size of the original image. So if the original image is this much, means I can develop this many number of, okay, if still the original image is very bigger, means I can develop more number of octaves and also more number of scales for the original image. So we generate several octaves of the original image. Each octave image size is half the previous one, right? Now So within an octave, images are progressively blurred using the Gaussian blur operator. So you can see right here, so it is more blurred, it is little bit blurred, it is blurred, okay, it is very clear, right? So as you go down, the blurring is increases. It is the effect that is resulted by the Gaussian operator. So within an octave, images are progressively blurred using the Gaussian blur operator. And blurring here is referred to as the convolution of the Gaussian operator, and the image resulting in the blurred image here. The same thing you can see here, right? So this is about the scale space. This scale space is consisting of the octaves and scale for each and every octave. So the octave may consist of like 32 real images or some amount of real images, which may be any kind of environment scene, okay, some like for example any kind of building scene or urban city scene, traffic scene, or whatever it is, and human faces, industry goods, anything, etc. So where each image may undergo with different transformation changes. So I cannot have the same view, right? So I can capture the scene with different capturing conditions. Like I can move the camera right side or left side. I can I can capture the scene in some lighting conditions. So I may have getting the different intensities, right? So that means each image may undergo with different transformation changes. That means here each and every octave is having many number of scales here, such that so many number of scales. So here octave may consisting of collection of 32 real images, which may be some scene, and each image may undergo with different transformation changes. So transformation changes are there, right? You can see. So these are the transformation changes, because I cannot find this space here, right? Okay, I cannot find this space here. So some kind of changes you can able to see with one image to one image. Okay, so what actually the benefit of the SIFT algorithm? It is useful for the object recognition or object tracking purpose by finding out the descriptors through the feature points in the given input image. So how it is happening, we'll discuss in step by step. So here I said you right, this is my first octave and this is my second octave. So first octave image size is double that of the second octave image size. That means the image size will be getting reduced half to that of the first image size in the octave. So in the first octave I will be having more image size, and the second octave the image size will be shrink to half, right? So octave equal to doubling of sigma. So here I have single sigma, here 2 sigma, single sigma, 2 sigma, single sigma, 2 sigma. So in this way it happens. So if still in the third octave, you can imagine what will be its value. And within an octave, the adjacent scales differ by constant factor k. So here k power of 0, k power of 1, k power of 2. These scales are the result of the Gaussian operator, which is blurring the original input image, right? Okay. Now what ultimately we have to perform here is, so let us assume if an octave contains some s+1 images, here, that means then can I write k equal to 2 power 1 by s? Like I will explain you. As the first image has scale sigma naught, right, and the second image has a scale k into sigma naught, k power 2 sigma naught, k power 3 sigma naught. It is k power of s into sigma naught, as this is my last image. So based on it, can I write now k power of s into sigma naught, this is the last image, means can I write k equal to 2 power 1 by s? So this is how it happens. Okay, now such a sequence of images, that means these are the sequence of images, are the results which happen with the convolution of the Gaussian Okay, so such a sequence of images convolved with Gaussian of increasing sigma, because it is k square, k cube, like that it happens, right? Of increasing sigma constitute called scale space. So this is about the scale space. So this is about my first octave. In the second octave, what happens? The sigma value increases, right? 2 sigma, and in the third octave the sigma value still increases, like this. So it is about the scale space where we can able to find the octave, and for each and every octave there will be a scale. Okay, scale of images. Now that means, can I say all these are nothing but L, which is nothing but L equal to G into I. So what is this G? G is nothing but it is a Gaussian operator, and I is the original input image. So this is one scale, this is one scale, one scale, one scale, one scale. Let us assume I am having here in this octave 5 images. So I need to perform the difference of Gaussian. So because these are the Gaussian results only, right? So if I perform the difference of Gaussian between these two images, I will be getting the result this one, and for these two the result is this one, and if I subtract the difference, if it will be this one. In this manner I can able to find out the difference of Gaussian for this first octave, for the second octave also, and for the third octave also I can able to find in this manner. Okay, so as I discussed, so if this is my original image, so the scale will be 0, and if the scale equal to 1, because for each and every adjacent images I said you the blurring increases. So this is k power of 0, this is k power of 1, k power of 2, k power of 3, k power of 4, in this manner, right? So k power of something, right? So as you increase the scale, the blurring also increases here. So that is what you can see. As you increase the scale like this, like this, like this, the blurring also increases. So this is about first octave only. Okay, now so the Gaussian function in 2D is g of x comma y comma sigma equal to 1 by 2 pi sigma square e power of minus of x square plus y square by 2 sigma square. This is the Gaussian function. Okay, so first point is what is my first step? I have to determine the approximate locations and the scale of the salient feature points. Okay, so what I have done, I found L, that is the result of G into I, where G into, it is not actually into, it is a convolution operator, that is refers to the application of a filter. So the Gaussian filter is, this is a mask, this mask is applied to the input image where I will be getting the L, some L function. Okay, now so after finding out the L function, what I am going to determine the difference of Gaussian. So the difference of Gaussian is nothing but the difference of the first scale to the next scale. So the first scale is k power of 0, the next scale is k power of 1. In this manner I can able to find, because DOG, this DOG is nothing but this is k power of 0, this is k power of 1 image, right? So k difference of the Gaussian into I of x comma y, this is the original image intensity. So L of x comma y comma k sigma minus L of x comma y comma sigma. This expression can also be rewritten in this manner like this. So difference of Gaussian, that is DOG, scale refers to the sigma of the Gaussian. So scale is nothing but it is the sigma of the Gaussian. Now G is the Gaussian blur operator, I is an input image, x comma y are the locations of particular point, and sigma is the scale parameter. So it is the amount of blur. Greater the value of sigma, so greater the value of blurring effect we can able to see. So finally I have to look for intensity changes using the DOG at two nearby scales. So this is one scale, right? So this is d of sigma, this is d of k sigma, this is d of k square sigma. So I have to find the intensity changes using the difference of Gaussians at two nearby scales. So this one is obtained by this one. So this is the one. So okay, this is the difference of Gaussian. Now I have considered the figure here. reconsider the figure which I have found in the earlier here. Now I have here difference of Gaussian for k sigma, difference of Gaussian for sigma, and for k square sigma. Now can I write compare a pixel x here with the 26 pixels in the current and adjacent scales? So this pixel x is surrounded by its neighbor by using 8-bit connectivity, right? So here I have 8 connections. This pixel is connected with its neighboring pixels. 8 pixels are connected with this x. And also in the upper image I have same 9 boxes. In the 9 boxes I do have 9 pixels. In the down image 9 boxes, 9 pixels. And how all these images? So I need to what ultimately I have to observe here is select a pixel x, and if it is larger or smaller than all the 26 pixels, 9 plus 9 plus 8, that is 26. The key points is the one ultimate aim for me to extract. So the key points are the extrema, which may be a maxima or minima in the scale space pyramid, because it is a scale, right? It is a pyramid also, because pyramid, what is the appearance of a pyramid? As you go up, the size will get reduced. Okay, so here also in the first octave coming to second octave, moving to third octave or fourth octave, what happens? The size is getting shrinked, right? Or it is compressing. So that is the property of a pyramid. So the key points are the extrema, which may be a maxima or minima in the scale space pyramid. That means it is a stack of DOG images where I can get both the location as well as the scale of the key point. So that is my ultimate aim here, that is approximate location and scale for the feature points I found here. Now initial detection of the key points. So if I have taken this one, this is my original image, and by using the SIFT algorithm, so the result of the step 1 of the SIFT algorithm will be this is. So these all are the feature points or the salient or stable points. This is the one that is the result of the step 1 of your SIFT algorithm. So inside this image, all the interest points or the feature points are placed at various locations of the object as well as of the background as well as the foreground. Okay, but I feel there are enormous number of key points, right? So how to overcome this enormous number of key points? We have to we have to filter it out, right? Okay, as we have generated a lot of key points. Some may be having bit low contrast and some may lie on edges, because the many number of key points are lying here on edges, right? Which is not so useful for me. Okay, which are not so useful as features or feature points. So I need to filter it out. The key point location and scale, we can interpolate it for more accuracy. Okay, that means we can do still more betterment here. So for this, what I will be using the DOG function, that is difference of Gaussian function, is expressed using a second order Taylor series. So what is the main purpose of it? Okay, that is we express the DOG function in a small 3D neighborhood around a key point by a second order Taylor series. What actually this is second order Taylor series, why we are employing here, we see. So this series expansion of scale space is deployed to get a more accurate location of the extrema. So more accurate location of the extrema means I think ultimately we are filtering out the unnecessarily traced out or extracted key points. So if the intensity at this extrema is less than a threshold value, reject it. So that is what we are doing here. So I am filtering out, for example, in the first stage I have got 10 key points, means if I have kept some threshold value, I can easily filter out such that I can get 3 or 4 key points or the feature points. Okay, Now the DOG, difference of Gaussian, has a higher response for edges also, of course. So edges also need to be removed. That means the key points which are also present on the edges have also to be focused here. How this happens? By considering the 2 cross 2 Hessian matrix H to compute the principal curvature. So let me discuss about that means here we do have 2 criteria. One is I need to remove the low contrast key points, and the second thing is if I have found more number of key points on the edges, so that has to be taken care of and filtered out. So that means the difference of Gaussian is expressed in the Taylor series. This is the mathematical expression, d of xi yi and sigma I. Yes, this is the entire mathematical expression for your Taylor series. Okay, so this first is giving you, that is gradient vector evaluated digitally at the key point. So this is the second thing is giving you 3 cross 3 Hessian matrix evaluated digitally at the key point. So to find an extremum, okay, because I need to have to get more better results, right? So that means in order to have what I will be doing here, to find an extremum of the DOG values in this neighborhood, set the derivative of d equal to 0. So if I have set d equal to 0 means ultimately this is the result I will be getting here. So just substitute this one here in the above equation. I will be getting, it is leading me to d extrema equal to d of xi yi sigma I plus 1 by 2 dou d of x comma y comma sigma transpose, and this is 1 x cap y cap sigma cap. So the key point location in this way one can update. So all the extrema with d extrema that is less than 0.03 are discarded as weak extrema. Some threshold he have kept here, nothing else, because what ultimately we will be getting, because this difference of Gaussian is also a number. I don't know what exactly that number is, because the difference of Gaussian is the result of the difference between L successive scales, right? Like this one, because the difference of Gaussian is L successive scales. Okay, but for G we do have one value, because Gaussian is a mask, first point. So for every mask, a mask is definitely carrying some values inside it. So whenever this mask is convoluted with the original image, of course the original image here also possessing some intensity or gray values at each and every location. So this is a number and this is a number. Whenever these two are being convolved, I do get here for the difference of Gaussian also a number, right? Okay, so coming back to here, I will be getting the d extrema in this case in like this. So the key points which have the d extremal that is less than 0.03 are filtered out here, are discarded, as they are the low contrast points here. So the same thing, because these all are the key points that are present in the homogeneous region, right? Here and here you can see all these points are filtered out as a low contrast points. But still I have left with here the key points that are still present on the edges, which are so irrelevant, like 1 2 3 4 in this manner, like that. So I need to again do some more activity here. That means here the key points which are residing on the edges are also to be discarded, because they are not at all considered as a salient point. As we know that the edge pixels will have contrast, okay, which are having the high contrast in one direction. That means the edge pixels may have the low contrast in the other opposite direction, right? So we compute here the principal curvature. Okay, so the principal curvature from the eigenvalues by taking Hessian matrix into the consideration. So how how it is happening, how it can be filtered out, we will see. Okay, so we have to ultimately reject the points with a strong edge response in only one direction, and only like by considering the Harris using the trace and determinant of the Hessian matrix. Okay, so what the operation follows is the SIFT uses the second derivative matrix. Of course, we know that the second derivative matrix is obviously a Hessian matrix. The eigenvalues of H will be giving a lot of information about the structure around the key point. In fact, the eigenvalues are the extremal and minimal principal curvatures of the surface, that is d of x comma y. So because I can treat this one as a surface, right? This is a surface, so I can able to find out the extremas. That means that because by using the eigenvalues which are considered as a maximal and minimal principal curvatures of the surface of the DOG function at that point. Okay, now computing Hessian of D, that is principal curvature, we use trace and determinant of the that is very much similar to a Harris corner detector. So in the previous lecture I have explained you about how to find out the corner points using Harris corner detector, right? Please go through that video once, such that the explanation, the further explanation will be very bit clear to you. So an edge will be having high maximal curvature but very low minimal curvature here. So you know that for an edge alpha, if it is greater than because alpha is a one eigenvalue, beta is one more eigenvalue. If one eigenvalue is greater than one more eigenvalue means what? It is ultimately an edge leading to a large value of this measure. So a key point which is a corner, that is not an edge, will have high maximal and minimal curvature. This is what it is saying. So of course for every corner we do have a large value of alpha, we do have a greater value of beta. Okay, so for the low contrast points, what we have done, the difference of Gaussian at extremas whose values, if it is less than 0.03, that means it is the threshold, are rejected. For the flat, that means it is considered as a low contrast points. So what about how to filter out the key points which are residing on the edges? That means the following can be regarded as an edgeness measure. So reject edges. So this is my Hessian matrix, dxx, dxy, difference of Gaussian. So derivative, x derivative to with respect to x derivative, partial derivative, x partial derivative with respect to y partial derivative. So dxx, dxy, dxy and dyy. So let alpha beta eigenvalue with larger magnitude and beta smaller. Of course, this is the definite condition for your edge, right? So the trace is nothing but sum of the diagonal element. So dxx plus dyy, principal diagonal. So alpha plus beta, because it is considered as an alpha, this will be beta. And what its determinant will be? Dxx dyy minus dxy whole square, that is alpha beta. So I will be getting here ratio. So trace of h whole square by determinant of h, that is alpha plus beta whole square by alpha beta. So let me consider alpha equal to r beta. What I will be obtaining, this is the expression. So this whenever the ratio, okay, so r plus 1 whole square by r will be minimum when alpha equal to beta, right? So will be minimum when alpha equal to beta, that means r equal to 1, can I say? Okay, now whenever the ratio, that means to check if ratio of this principal curvature, if it is below than some threshold, okay, so we just eliminate. So eliminate key points if the ratio is greater than 10. So that is what we are doing here. Okay, so to check if the ratio of the principal diagonal curvature is below some threshold here, as it increases with r, okay, because if r increases, the ratio is increasing. So eliminate the key points if the ratio is greater than 10. That means if the ratio is greater than some threshold, I can neglect the edge response here. That is what happening. In this way, I can easily filter out the key points which are residing on the edges. So this is the ultimate image result what I will be getting after applying the Gaussian matrix. That means by employing the Gaussian matrix. So many number of key points are found here, right? So these were discarded. So you can see here successively they are found, but here I don't find that many key points when compared to this image. Okay, after this one I have the third step, that is orientation assignment. What actually it is orientation assignment it is doing here is, so now that means we need to determine the orientations for each and every key point. So where we have a good points, many number of good points here from this image. So choose a region around each point, remove effects of the scale and rotation. So the scale and rotations are not considered. So what the effects one can get from the scale and rotation, those are ignored. That means our ultimate aim is to find out its orientation for each and every key point. So determining the orientations for the key point. So this is the one how you will be getting, you know, right? L equal to G into I, the convolution with I. Compute the gradient magnitude and orientations here in a small window around the key point. So that is what here it is doing at the appropriate scale. So appropriate, okay, using the finite differences. So in this manner I can able to get the magnitude as well as the theta, that is the orientation direction theta. So L of x plus 1 comma y, because this is entire thing is the expression that is considered by adopting the finite differences, right? L of x plus 1 comma y minus L of x minus 1 comma y whole square plus L of x comma y plus 1 minus L of x comma y minus 1 whole square. So this is the expression that is obtained by considering the finite differences. Okay, and this will be my theta, that is direction, the key point direction, orientation. So an orientation histogram with 36 bins covering 360 degrees is created, because if this is a small region means that means it is a circle or it may be an ellipse or whatever it is, definitely it is possessing 360 degrees, right? So this point is wrapped by a curve. That means the curve, that means everywhere the points 360 degrees, everywhere something is being wrapping this point. Okay, that means a orientation histogram with 36 bins covering 360 degrees is created. Okay, so why here only 36 bins in the histogram is considered for the 360 degrees of rotation or view is, in the histogram image I have 0 to 9 1 bin, 10 to 19 1 bin. That means each and every bin is having 10 as its capacity, right? 10 plus 10 plus 10 plus up to how many number of tens? 36 number of tens, or 36 number of bins I am having. Each bin is starting with 0 and ending with 9 degrees. Okay, that means 10 degrees each bin is carrying here, 10 degrees. So degrees is nothing but the directions. Each bin is carrying 10 directions or 10 degrees. So the gradient direction at a certain point in the orientation collection region is, if it is found 18.759 degrees, then what is the nearest degree assignment I can give to it is, then that is 10 to 19 degree bin. So I do have the 10 to 19 degree bin, means this point whose direction is 18.759 degrees. Okay, because you know about the protractor, right? Okay, so if it is 18.759 degrees means that direction the point is moving, the vector is moving, means I will assign that vector comes under the category of 10 to 19 degree bin, this bin, second bin. So once you have done this for all the pixels or all the key points or the salient points, the histogram will have a peak at some point. Okay, so this direction has to be considered for that particular key point. Okay, so the same thing I will explain you clearly. So this is the circular region, okay, as this is the one. Okay, this is how we are wrapping a key point with a circle. So this is my region. Okay, and assign the dominant orientation as the orientation of the key point. So here among all this, because I can find only 8 number of bins such that each and every bin is pointing towards one direction, like north, east, northeast, northwest, west, southwest, south, southeast. So all the 8 directions. So that means I can say that the image, because I do have a point, this point is being wrapped by a curve here, which is a circle, and this region is accommodating many number of points which are having its own direction, assume. So that means this entire region is having many number of boxes, and each and every boxes is showing it's a particular own direction, like north, west, northeast, north, south, west, southeast, like that. So all these are transformed into a histogram graph. So these are the number of counts in this direction, and these are the number of counts in this direction, and this is the number of counts in this direction. So the number of boxes which are like orienting or directing towards the west side are higher here. That is what this graph is showing us the information. So assign the dominant orientation or the orientation of the key point. So in case if if multiple peaks are there, so if suppose these 2 peaks are there, this one and this one, or that means these are the multiple peaks or histogram entries. Of course these are the histogram entries which are of 80% of peak. If this is my 100% means this is obviously an 80% of peak. So for which we have to also create a separate descriptor for this orientation. So for this orientation I know how I will be creating a descriptor, but for these 2 different orientations also I need to get or create a separate descriptor. Okay, now histogram of gradient orientation. So the bin counts here, the bin counts are weighted by the gradient. So the bin counts, this is the bin counts, like 1 2 3 4 5 6, it increases, right? The count increases. The bin counts are weighted by the gradient magnitudes and a Gaussian weighting function. So these are the gradient magnitude, right? Usually I have said you that here of course we have taken 8 bins into consideration, but generally in practice we need to consider 36 bins into consideration. So usually 36 bins are chosen for the orientation. So in this manner it happens. So the same thing. Now the last thing is here we are left with is the determining the descriptors for each and every key point. So my ultimate is the key point descriptor. Okay, so a small region I will be considering around a key point. So this is my region around this key point. Now because this key point is located somewhere here, so this is my region. Okay, this region, this is the region, and somewhere key point is there. Okay, so this region is wrapping many number of boxes, or you can even call them as a pixels, and each and every pixel is having certain orientation. So this is my image gradient, where I can see gradient orientation histogram also, as in the last slide, in each cell. So divide this region into n cross n cells. If n equal to 2 means 2 cross 2, 4. So each cell is of size 4 cross 4. So this is my 1 2 3 4 2 cross 2 cells, and each cell is of 4 cross 4 size. So 1 2 3 4 1 2 3 4 4 cross 4 each cell is. Now by using this one, I can still develop the gradient orientation histogram as how we have seen in the last slide. So each histogram entry is weighted by the gradient magnitude and the Gaussian weighted function with the sigma equal to 0.5, that is half times the window width. Sort each gradient orientation histogram bearing in mind the dominant orientation, because anyhow I have to find only for the particular key point the dominant orientation, the dominant direction of the key point only I need to find out. So for this one, this is my descriptor for this cell, because it is a 2 cross 2 cell, right? So for this cell, this is my descriptor. For this cell that is accommodating 16 boxes, this is my descriptor, and for this cell this is the descriptor, and for this cell this is the descriptor. So that means the arrow is very long, means many number of bins are in the direction of southeast. So that is what it is giving. It is the descriptor. Okay, so how this 128 dimensional shift descriptor is formed? So let us discuss how this is happening. Okay, so we now have a descriptor of size r into n square. If for suppose r bins in the orientation histogram, so in this case what we have considered 8 bins, right? So if r bins in the orientation histogram, so typically a SIFT algorithm uses 8 bins and n equal to 4. So n equal to 4 means can I say 8 into 4 square, that is 16 into 8 128. So why it is like this? Why n equal to 4? I have 8 bins, that means 8 direction. For how many cells? For how many cells? 1, 2, 3 and 4. For 4 cells I have considered. It is the general working operation for a SIFT. That means the SIFT here employs or it operates by considering into account the SIFT uses 8 bins and 4 cells. Okay, 1, 2, 3, 4. So the length of each descriptor will be, that means here the length of each descriptor will be 128. So the descriptor is invariant to rotations due to the sorting. So in this manner it is invariant to the rotations. So that is what it is happening. It is a 128 dimensional SIFT descriptor. So let me recap the whole thing what we have studied up to now. So in the key point descriptor, as each key point has a location, scale and orientation, so to compute a descriptor for the local image region that is very distinctive and invariant. So to do this, what we are taking here into consideration, of course this is my final result, key point descriptor, the same thing, key point descriptor, that is 4 cross 4. Okay, that means 16, right? Okay, so it is a 4 cross 4 descriptor. Okay, so to do this, a 16 cross 16 window, because 1 2 3 4 1 2 3 4 1 2 3 4 1 2 3 4 16 vertical and 16 horizontal. So this is the region that is wrapping 16 cross 16 cells or tiny cells or some mini cells. Okay, so to do this, a 16 cross 16 window around the key point. So here this is the region and this is the region what being enlarged is taken, and it is divided into 16 sub blocks. So these are the 16 sub blocks, right? 1 2 3 4 5 6 7 8, and each and every sub block is of size 4 cross 4. So for each sub block, okay, that means here for each and every sub block 8 bin orientation histogram is created. So this is the one block, one block, one block, one block. So for each and every sub block 8 bin orientation histogram is created. Okay, because this is the 8 bin orientation histogram, right? So 4 cross 4 descriptors over 16 cross 16 sample array were used here. Okay, that means this 16 cross 16 window is converted into a 4 cross 4 descriptor only, right? That means for 16 cross 16 sample array, because it is an array, a collection of many number of pixels. So around this key point is being wrapped by the yellow color. So yellow curve, this yellow curve is some region that is accommodating 16 cross 16 window or cells. Okay, that means here this 16 cross 16 is having how many number of blocks, sub blocks, 1 2 3 4, that means 16 blocks are there. So each and every sub block is using how many? 4 cross 4 discrete. So each and every sub block is using 8 bin orientation histogram. So if you consider this one, like for example, if you consider this one, this is the result, right? In this manner you need to analyze. So 4 cross 4 descriptors is the result, key point descriptor for this 16 cross 16 sample array. And finally, now can I say this is my 4 cross 4 and each and every box is having how many number of bit? 8 bins. So 4 cross 4 cross 8 directions, or bins are nothing but directions, gives 128 bin value. It is represented as a feature vector to form key point descriptor. That means every key point is represented by using a feature vector, that is a key point descriptor, which is of 128 bit length or 128 bin values. So this is my final, each and every point is a 128 dimension feature vector it is. So this is how one can able to find out the key point descriptors in the SIFT algorithm. Okay, so the main applications why we need to study the correspondency between the images have to be developed, right? As I said you, the SIFT is invariant to the affine transformations. Okay, so the SIFT here mainly used to extract the stable or the salient points in the given input image. So the future points which are extracted by using the SIFT are maybe used for image alignment. Okay, that means panoramic stitching, as I said you, right? Aligning left and right image in the stereo vision, and by finding the correspondency. Okay, so by finding the correspondency, and it is also used for some 3D reconstruction, also motion tracking, object recognition, you can see. So this is my object recognition, and index and robot navigation, all the things. We have a many number of applications like in the object recognition, you can see the input. For the input what I have given, I just given here the some reference scenes, some kind of a database of scenes of many number of scenes are provided here, and each scene is having its own unique label, like object name, or it is having its own pose, or whatever, it's its own scale kind of thing. So the second input what I have given here is a image that is to be tested, in which I have to locate where the scene is present in the given second input image. Okay, so these are the 4 scenes, and this is my second input image, where exactly these locations are placed or found will be like recognized in this second input image. That so the SIFT can easily able to do the recognition process. So these are the advantage of a SIFT algorithm, like test of illumination robustness, also same image under different lighting conditions or illuminations. Okay, where still I can able to find what the object is. So object tracking, mobile robot, object recognition, 3D matching, or whatever, these plenty number of applications are there by using the SIFT algorithm. Okay, so we'll end the session for today. and thank you. Have a nice day.